Hello. Hello.
It gives us great pleasure to invite Dr. Minhaz Hossain of the Department of Physics, IIEST Shibpur, to the weekly our department. Has BSc and MSc degrees in physics from Department of Electronics and Telecommunication Engineering at Yadavpur University. Has also held visiting positions at University of Trento in Italy, State University of New York at Buffalo. EAD students for their doctoral thesis in the Department of Physics, IIEST Shibpur. So I invite Professor Hossain to come and talk.
And thanks to the Department of Physics, especially Professor Mathieu, for inviting me and giving me a scope to interact with young people like you. Uh, actually, today I'll talk about something that is related to mainly my research work, but I like to start from almost the BSc level. So I have divided this talk into three parts. Okay? First, a basic theory. Then, yeah, you know the topic was like surface states in nanoscale, problems and prospects. So, nanoscale is known to everyone today. So, I think it doesn't need any explanation for that. So, here I'll show you some applications of surface tests where it can make more sense, better sense. Actually, I'll show you that surface tests are pillars in devices, electronic devices, solid state devices, normally. But you can always treat a killer like a so joy and guilt, outlaws, right? So happens to have used them in a different way. Similarly, are smart enough to use outlaws for something good, then surface sets can also be used for something better for device physics in the nanoscale. Talking about solid state devices. So devices are primarily electronic devices. So what we have to do? We have to deal with electrons in a solid. And in a solid, electrons are basically governed by the Schrödinger equation. So what is a solid? Solid means we mean actually crystalline solid. So crystalline, what is a crystal? Crystal is nothing but a lattice along with the molecules or atoms or ions sitting there, the lattice points. So it gives you a periodic potential. And at any finite temperature, you know that the crystal vibrates. Okay? And crystal vibration will definitely lead to one dimension just to understand things. So this potential, you understand that if you have a potential, periodic potential, that can always be expressed in Fourier component. So you can express in this form, vi cos gix, where gi, if you take g0, it will be just twice pi by a. If you take I equal to 1, then 4 pi by a like that. So this is actually the model of the potential. And to make life more simple, what happens here? At the atomic size, you have the singularities. So if you look at the potential at the atomic size, you have. But when we are dealing with electronic devices, we actually deal with valence electrons. Valence electrons never feel this singularity. They go from the outside of the approximation is a good approximation to deal with electronic behavior for solid state devices. So it can be considered as a smooth function. So that concept is the pseudo potential thing. Now what you do, we are just scaling the distance with unitless z instead of x. We are taking it as a pi x over a, such that just dimensionless Schrödinger's equation we can get, and energy in terms of this in the units of h square pi square over twice m square, which is the energy of the particle in a box with length a. Right? H square pi square divided by twice m square is the energy eigenvalue, ground state eigenvalue, ground state energy of the particle in a box problem. That unit we are representing energy, and this is the potential in the same unit. Okay. What happens if you write that? You just replace this. If you do these substitutions, then the Schrödinger's equation becomes this one. Okay. Psi double prime z plus p minus 2q cos 2z psi operating on psi gives you 0, and this is called Mathieu equation. So around 300 years back, French scientists that. And if you try to solve this equation, what will you find? You find the solution space has got two regions. The gray regions are the unstable solutions, and the white regions, give you the stable solutions. What does it mean? Stable solution means, there is no divergence. The solution will be periodic, not work here because here the main potential in WB it has a slow function. So to have a three box and there is a high frequency oscillator. So it's another way. So it's better we do it in like connectivity model that gives you the band structure, and we have in connectivity model we assume that the solutions, the trial solutions are plane wave modulated by the crystal. That was the assumption that you plug into the coordinate solution. But here what happens, you don't have to go for any assumption. Just write it and go for the solution. It automatically gives you the plane wave kind of solution modulated by a crystal potential. Right? So Bloch theorem is embedded in the solution. You don't have to do that. Okay? What are the answerable solutions? It is a periodic function, something like sin kx multiplied by an exponential term. Either that increases with position or decreases with position. So if you start with some small value of psi, it can blow up to very large value, or if you start with some non-zero large value of psi, then it will decay down. Okay, for this one. So these are actually the problem is a crystal by definition goes from minus infinity to plus infinity. Right? There is no transition for ideal crystal. Actually, if you have a big large crystal, then we don't think of the surfaces. Okay? I'll come to that later. So theoretically, your wave function should be normalized, right? So if you have a anyway kind of solution, so if you want to normalize, what you have? You have e to the power IIEST type solutions. So e to the power multiplied by e to the power minus IIEST gives you a constant, right? So it is normalizable for k waves. But when you have a diverging term, this term, what will happen? For infinite crystal, it will always diverge. So you will not be able to normalize your unstable states. So that's why for real and ideal crystal, we think we don't consider the solutions corresponding to this. Then the band gap comes into play. Look, what is there in the x-axis? Q is the V0, right? And here is the energy. So if you have a crystal with some value of Q, which is the amplitude of the periodic potential, then what happens? Just let me draw a point, a line for a fixed value of V0. Say here I am fixing a particular V0 and I am drawing. Consider this as a state. Okay? So what happens for a particular V0? This is the unstable region. The solutions are not acceptable. Then here you have some acceptable solution. So these values of E are acceptable. Then unstable. That means these values of energies are not acceptable. So you get the band. Then again these are acceptable. Next band, next acceptable band, next band like that. So you get band gap, acceptable band gap like that. Okay? What we get in chronic penny model. The same thing you are getting in a different way with some advantage. What is the advantage? In chronic penny model, we don't talk about the unstable solutions. So normally, in normal, up to BSc or MSc first year, second year, when you are not in research, you don't talk too much about surfaces. Because those unstable solutions are never considered because they are not normalizable. So you don't accept them for ideal crystal. But what happens for finite crystal? If you have a crystal which is finite, then what happens? The problem of divergence of the integration psi star psi does not come into play, right? So it is normalizable.
So actually the limit of integration is u.
Yes, here in actual crystal, ideal crystal, you have to integrate from minus infinity to plus. Only if you have linear solutions, that will give you a constant value. an electron corresponding to this case, what will be the value? Look, this is symmetric around 15. So it will be L by 2, right? So half of that. So 30 will be the, so that means if you try to find an electron in that state, most of the time average value will be in the middle. But if you think of this state, it will be at the one end, right? So at the surface, right? So that's why you can identify the solutions of Mathieu equation corresponding to the unstable solutions are basically, you can identify them as the surface states. Because the expectation value of position is near the surface. If you take the plus sign, then in this surface, at the right surface, and if you consider the minus sign, then it will be on the other surface, right? So these electrons on the unstable wave functions should reside near the surface only. Now, if you have a crystal of say 10 centimeter or maybe 1 centimeter, then the surface, how many atoms are there at the surface? Very little with respect to the bulk atoms, right? In the bulk you have 10 to the 23 of the order of 10 to the 23. At the surface you have at least 10 to the 10 order of magnitude lesser atoms. So we always neglect the surface effect in bulk system. But you cannot do that in the nanoscale. I'll come to that a bit later. Before that, let me show you that these mathematics can be actually visualized very easy. I want to show you that. Actually, 2-3 years back, I showed this setup also through online mode. So again, and these students are going not there. That's why I kept it. Just think of a simple thing, right? The equation of motion is d2x dt2 plus. Now you can understand that if you write the particle in a box problem without, the particle which is free within the box, you will get d2 psi dx2 plus k square psi equal to 0. Exactly the same mathematical form if you replace psi by x by t and k by omega. Right? But there is a big difference. Can anyone tell me what is the big difference between these two equations? Schrodinger's equation for free particle and this one, the equation of motion for x and y. Mathematically, they look very similar. What is the basic difference between them? Yeah, this is
maybe it's function of time and maybe it's function of position.
Yeah, that's true. That's definitely mathematically, time is a variable, position is a variable. So mathematical difference is not here. But the difference lies here that Schrodinger's equation is an eigenvalue equation. It's a boundary value problem. And here this is an initial value problem. So if you keep this thing in mind, you have to keep this in mind that this difference exists there. Otherwise, they are very similar. Okay? And also one thing will be there that T in our known universe, we don't know that T goes in the opposite direction. There is an arrow of time. But X doesn't have. So that difference is also there. So here the solution is A sin omega 0 t plus B cos omega 0 t. And just replace psi x by psi and t by x and x sin kx, B cos kx, like that. So that's the same thing. So equivalent plane wave solution you can get here. So this is Schrodinger's equation for free particle, and this is harmonic oscillator, simple pendulum under pattern. Now let us do simple modification. Just let us consider that the bob of the pendulum is a magnet. Okay? And put current carrying coil like this, such that the magnetic field will be in this direction. Right? So there is no current flow. So now if you connect find it, but just raise your hand or take my attention and ask your question. Okay? I'll stop and I'll try to make it as clear as possible. So we can write the G effective as the original G multiplied by, H cos gamma t, where H comes from the number of turns in the coil and potential applied, all these things. Okay, so it's lumped into this constant. Okay, so this, if you put H equal to 0, that means if you remove this thing, then we will come back to our original semiconductor. And depending upon this H, value of H, how strong this is, this coupling constant will depend on that. Now, what is the effect? Just this thing. G will be replaced by G effective. And B2x, B2 plus G by L, this thing, So this is exactly equal to, the same equation is given to us. Okay, the same equation, but it is actually, look at the Schrödinger's equation in periodic potential, one-dimensional potential. Exactly equivalent to that. There is a slight difference, that this is plus and this is minus, but that can easily be eaten up by the phase curve. Somebody is there, so when you are starting your clock, whether it is pulling or pushing, that will give you the plus sign or minus sign, right? So it doesn't matter. Now, here is a setup. The setup is a real one because we have a magnetic force. So this stand, and there is a, have you seen loudspeaker? The back of the loudspeaker will be a ring magnet. So that ring magnet is used as a ball. Okay? And this is the Helmholtz coil. You can go to physics lab and you will find such things are down somewhere. So just grab one and put that and connect it to a function generator. Okay? So you get a math. So this is a math oscillator. I'll show you two different types of solutions. If you just do a little bit of mathematics, if you consult the book of Lambda analysis, one mechanics, that series. Okay, so you will see that there is a simple treatment to show that in this math oscillator you can get parametric resonance. It's not normal force vibration, resonance in force vibration. In force vibration, what happens? You apply a periodic force in the direction of oscillation of it. And if the frequency of the oscillator and the frequency of the forcing system, they match, then you get velocity resonance at exactly the same value, and amplitude resonance occurs very close to that, depending upon the damping time. Here, the story is a little bit different. Look, the oscillation of the pendulum is in the horizontal direction. The force applied is in the vertical direction. So, no component of the force acting in the direction of oscillation. But what happens if the value of gamma, that means the frequency of the external frequency that is changing the oscillation frequency, that gamma is twice omega 0. Omega 0 is the natural frequency divided by n. That means when it is twice omega 0, when it is omega 0, when it is omega 0 divided by 2 omega 0 by 3, or omega 0 divided by 2, these kind of values, then what happens? Resonance takes place. Resonance means the amplitude will increase with time. So let us see what happens. And if your gamma is not close to this value, then it will be solutions. So I am showing you two different cases.
So this resonance will give you the surface tension.
Yes. Yes. Yeah. Just I am showing you the videos. এটা একটু দেখাচ্ছে নাকি? So actually, if we look at anyways, so look at the oscillation of this pendulum. You can track the position as a function of time. The stable solution. So here we purposefully have chosen the length in such a way that the condition for parametric relevance is not satisfied. So we are getting the stable solutions. Okay. Now here what happens? Look, the displacement is increasing and displacement is oscillating with time, changing with time, which is equivalent to psi in case of coordinate equation, and time has to be replaced by position. So exactly this is x versus t that has to be translated into psi versus x if you want to make the analogy between this state and stable state of Mathieu equation in the context of coordinate equation. Now let me remove it from here. I don't know how can I do that.
So for the surface state,
Yes.
the phase space trajectory will be just outwards point.
Yes. Yes. I'll come to that. Exactly. Now look at this. We have purposefully set the omega 0 to that, gamma is equal to omega 0 over n, that is satisfied. Okay. So look, it is actually increasing with time. And as you correctly guess that it will be a spiral out. The reverse hand. It is reverse hand. Okay, that's opposite to time. Actually, nowadays you see, wall clocks having electronic wall clocks, digital, not digital, but electronic wall clocks having pendulum, and that pendulum runs for 2-3 months. You don't have to, just one battery is needed. And if you look at the backside of the pendulum, you see exactly this kind of arrangement is there. It's not a case of force vibration. This is Mathieu oscillator, and this is increasing part. The exponentially increasing part is calculated in such a way that it compensates the damping. Okay? Air damping, such that it can run for months. So this unstable state is basically the surface state.
So this equation can be mapped to first order equation. Can be
Yes,
compressed to first order.
definitely.
And then you will never get the limit cycle kind of behavior kind of surface.
Yes, possible. Because if you consider both, if you consider the gamma mean, the frequency part, and if you include a damping. So these two solution is kind of what? Show that again. Display setting কিছুটা সাইডে ব্যাপার Yes. So now look at this point. So gamma is equal to 2 omega 0 over n, right? What is gamma in the context of the solid? Gamma is G0, right? Gamma is the frequency of frequency which is cos Gx, right? So G is the gamma. And what is omega 0? The periodicity state in space that role is played by k. So actually equivalent relation is G0 is equal to 2k over n. Now what is G0? 2 pi by a. Plug in that value, 2 pi by a is equal to 2k over n. So what is the k? N pi by a. So can you identify this guy? N pi by a, the zone boundary, plus minus 1. So that is where you will get the unstable solutions.
So this is basically the
Yes, within the discontinuity. So at the Minhaz Hossain and there is a gap, then the conduction band starts. But in between, you are going to get this unstable solutions. So at the Minhaz Hossain boundary, you are getting the unstable states. If you take the expectation value of position corresponding to those states, they actually these unstable states are nothing but the surface states. So in this way, theoretically, you can understand what we actually mean by surface states. So summary of this part gives you this. So you have the valence band, the conduction band. In between, you can have surface states. Okay. So this is the EK diagram. In between, you can have surface states within the band gap. So if you look at for any finite crystal, if you are near the surface, band structure is not, it doesn't give you exact band gap value. You have some states falling within the band gap. Always there will be some states falling within the band gap that you cannot ignore. And these are actually, try to avoid surface states. So surface states are coming from defect. Why is it so? Because crystal, ideal crystal has got, infinite extent, but you are truncating. So truncation is a, you are actually introducing defect. One, atom from the lattice that will give you defect. Okay, different types of defects you know. So those defect states actually fall within the band gap, which are actually surface states are also defect states. Now, for electronic devices, a basic building block is p-n junction. If you want to make a transistor also, you need p-n junction. So p-n junction means you have just added to n and p type semiconductors such that you have a band bending there. In the reverse bias condition, the current that we get, the reverse saturation current that we call, is actually due to the minority dynamics. That means the holes, in the reverse bias, the electrons will come from the p side to the n side, and holes will go from the n side to p side. But if if you have a lot of surface states within the band gap, what happens? You know, if you apply some voltage and you have some defect states which have already captured some electrons there or holes there, they will come into play. They will cross the junction and give you some current. Okay, so for PN junction with surface states or defect states within the band gap, you don't get a very good diode. You get the reverse current, something like this. If you apply voltage, the current will increase.
So the order of magnitude of this reverse current
Depends on the density of surface states.
usually in micro
Per centimeter square. Yeah. Or in nowadays, we can produce very good crystals, so nanoampere is the thing. But it can go to milli, I mean not milli probably, but 0.1 milli. If you apply 10 volt or 12 volt, it goes like that. If you perform this simple experiment with a voltage, it will never remain like this constant of voltage. It will increase because of the surface states. So actually, then your diode will know we are very good rectifier. Okay. So and a transistor will not be very good transistor. So the logic circuit that we use that we do using transistor will not be very good transistor. So not only that, for solar cell also, what happens? You know how solar cell works. You have a PN junction, you shine light, you create electron hole pairs. So electrons from the p side will easily go to the downhill. Okay. Downhill for electron, you generated some electrons here, so they will go there, they will accumulate here. And the holes, this is the downhill for holes. So holes generated here will be accumulated there. So p side will be positively charged and the n side will be negatively charged. So it is acting as a battery. Now we connect external circuit, current will flow. Now if you have surface states in the middle of the battery, they will cross, some of them will cross, but some of them will be captured here. Okay? And if they are captured, you are not going to get the photovoltaic. Surface states are also detrimental to the efficiency of the solar cell. Now, light emitting diodes, nowadays what we see as domestic lighting device also, light emitting diodes, they are also the surface states play as non-relativity recombination center. So what do you mean by relativity recombination center? One electron recombines with a hole and gives you a photon of suitable energy. That is relativity recombination. But the surface states and defect states, you injected some electron or hole, they are not recombining with each other, rather going into the defect and give the extra energy that will be given to the electrical source that will be used as a heat generating system. Okay, so light emitting diode, efficiency of light emitting diode will decrease. So the surface states are basically killer. They are the killer in electronic devices. Okay, so they are present in any finite crystal near the surface. Okay, if you however, they vanish within the path because the exponentially decaying. So the expectation value is near the height near the surface, position expectation value is close to the surface, and within the path the value is less. So for a big crystal, large crystal, normally micro crystal or millimeter size, centimeter size crystal, we actually bother too much about the surface states if we have reasonably pure semiconductor and one crystal of suitable size. But what happens in nanoscale? What do you mean by low dimension? Low, high, big, small, these are all relative quantities, right? So when you are talking about low or large or small, you have to refer to some characteristic level. Okay? So it actually depends on different property. If we talk about electronic property, the de Broglie wavelength is the characteristic level. So if your system size is few order of magnitude larger than the de Broglie wavelength, then the electron does not fill the surface. Okay? So for example, if you have a peanut in the middle of hidden one, calculate for silicon, the excited years is around 5 nanometer. Okay. The de-Broglie wavelength at room temperature for silicon is of around 8 nanometer. Okay. So if the system size, this semiconductor crystal size is of the order of 10 nanometer, then we call it nanoscale. Why? Because if you have a semiconductor of say 5 centimeter and if you reduce the size to 1 centimeter, no property will change almost. But if you have a semiconductor with say 10 nanometer and you reduce, how much difference is that? And when you are talking about chemical property, actually surface to volume ratio, chemical reaction takes place at the surface. So surface to volume ratio becomes important. So if you actually decrease the size, what happens? Look at this. The surface atoms and bulk atoms. So if you are in a small size, number of surface atoms is more than the number of bulk atoms. Right? So at nanoscale, surface states cannot be neglected. Okay? They are, they are living material. If you are doing research in nanoscale, you have to deal with surfaces, and surfaces are killers. Okay? So they are the outlaws. And let me show you one interesting result from one of my PhD students. So actually this is two students. So normally what happens? This is a sample that contains silicon nanocrystal. Okay, contains with a tube head. And here we are shining the same sample with UV torch. Look, there is a green light and there is a red orange light. Okay, so what happens? The green light is coming from band to band transition, and the red light is coming from the surfaces.
That's why wavelength is high.
Yes. So you are getting two different types of luminescence coming from the sample. So in presence of surface states. Now, this is a standard way to distinguish between radiative light transition coming out of band to band transition and defect limited transitions. What is that? Look, normally in semiconductors, surface state density is much smaller than the band states, normal Bloch states. Bloch states are coming from number of atoms. So, you have Howrah number of atoms. So Bloch states are of the same order, till the 23. But surface states are dependent on they're lying on the surface, and not only that, you have actually, if you have less defect, then less state. So if you increase the intensity of incident intensity, then if the light is coming out of defect states, with increasing intensity they will saturate. Because you are shining with more photon, but you don't have that much defect states where you can pump them. Right? You get it? Because you have very small number of surfaces. So with increasing, the output will saturate. It will not increase like linearly. But if it is coming from band to band transition, it happens the other way. So if you increase, if you give more, if you shine with more photon will come out. It will be linear. Okay? But the result is just opposite in case of nanoscale. Look, this light, this green light is coming from band to band, and this red light is coming from surface states. Look at the intensity variation. This P2 is the high energy. The high energy is the band to band. The band to band is saturating faster than the surface states. Why it is so? Just in the previous slide. You have more surface states than the bulk states. So the properties are primarily governed by the surface property, not the bulk property.
So if you have any the population of the surface states towards the band state, so then only you can use that.
No, actually, surface states are not actually that much in our hand.
No, but you can experimentally control the
size you want. You want to, if you like, you can shade. I'll show you. You can switch off the dim light and get the red light, or you can do the other. Now, is there any advantage of the surface test that can be explored? That is the last part of my talk. I will take around 10-15. I have already lost the time to this. So, in 4 different situations, I will show you how you can. Now, I have already told you about intermediate, the solar cell, non solar cell. So, if you look at the spectrum, solar spectrum that comes that falls on our Earth surface is something like this. You know, the silicon band gap is of the order of 1.1 electron volt. That corresponds to 1100 nanometers. Okay. So, if you have a photon that whose wavelength is more than 1100 nanometer, that will not be able to create any electron volt pair in silicon. The 95% solar cell market is of silicon material, right? Whose band gap is 1.1 electron volt. So, this range of photons which are coming from solar, from the sun, that is actually just getting transmitted to the silicon solar cell. That has got no use in our electricity generation. But if you can make some states within the band such that, say, 2 such photons in 2 steps, the electron will get excited from the valence band to the intermediate band, and from the intermediate band to the conduction band. Then 2 photons were actually both were being transmitted, but now 2 photons are generating 1 pair of electron and hole. So then you can get more current or voltage in the. But there is a condition that this intermediate band should be electrically isolated. Otherwise, the voltage that you get from the solar cell will be used. So that has to be created everywhere. Now I am showing you one experiment. Here this is called PECD, plasma enhanced chemical vapor deposition. If you apply and if you use silent gas and nitrous oxide together in plasma chamber, then silicon, non-stoichiometric silicon, this is called SiO2 is the silicon dioxide, but here X is less than. That means SiOX is silicon rich silicon oxide. It's not in proper stoichiometry. So if you generate that and heat it up, then what happens? They will try to get the stoichiometry SiO2, how silicon rich, so some silicon will be released, and those silicon will create nanocrystals. Okay? So here it is. Can you see? So this is silicon oxide matrix, and everywhere you get the lattice planes of silicon. These are called silicon nanocrystals. Look at the scale. This is 5 nanometer. So we have 5 nanometer, 7 nanometer, 2 nanometer, 3 nanometer, such kind of. Now what we did, we made a device, PIN device, where the active layer is a silicon dioxide layer. Okay? I am not going into that, details of that, and this is a setup. It's not very tricky. You are measuring the current and voltage characteristics, and you are shining with suitable light. Okay? So that gives you the spectral response. Look at the spectral response. Within the visible region and within the band gap of silicon, you get milliampere per watt kind of spectral response. Light is falling on that, you are getting some current. Okay? And if normally if you have bulk silicon, if you have incident wavelength more than 1100, you don't expect any current, right? But here in this sample, look at this, you get very little current because of the surface cells. Okay? And not only that, if you it's a reverse current. I mean the photo current. If you talk about solar cells or photodetector, and we are shining with this is corresponding to nearly 1400 nanometer, which the energy is less than the band gap of silicon, and we are getting photo. Okay? Why it is so? Because the silicon nanocrystals contain surfaces, and those are giving photodetector. And very interesting. close to minus 1600. Okay, so minus 1600 plus 0 gives you minus 1700 or something like that. So 0 and 100 are equivalent. How it is possible? Because of the same thing that we have already discussed. Look here, when you are applying only 1200, okay, then what happens? You can generate from here to there, but not from here to there. Okay, from the intermediate to the conduction line. But when you are generating applying blue light, you are generating some electron volt pairs which are captured at the intermediate bands. Now when you are applying 1200, then the captured electrons are jumping from the intermediate band to that. So slight increase in photocurrent can be achieved by this kind of structures. Now in our laboratory we normally generate, you see this one is silicon quantum rods. Rod means the aspect ratio is not spherical. It's one side is elongated, the other side is a little bit shorter. So you can see by electrochemical etching we can generate quantum rods like structure. Here you can see the rod like structure. These are the rods standing on the silicon wafer, and it has got some oxide also. And these samples also, if you have heard of AFM, atomic force microscopes, there is a nice instrument that shows the surface topology. We have used that atomic force, peak of the atomic force microscope as electrical probe, and it shows switching in the single nanocrystal. By this AFM, you can see single nanocrystal. Okay, and we have probed single nanocrystal, and we have set some current, and we measure the voltage current characteristics, and we get switching here. Switching, and then in your BSc you have studied tunneling. So tunneling gives oscillation kind of thing. So here it goes like this and then oscillates. So you can here also you can see some oscillations. Here look at this. Because when you get switching, then there is an oxide layer. So thin layer means tunneling takes place. So that tunneling gives rise to this kind of oscillations. And when we focus on the average nanocrystal material, we have got two very nice results. One is by controlling the surface state density, you can make your device from non-ohmic to ohmic to rectifier. So look, we have just increased the temperature. This is at room temperature. The IV characteristics for this sample is non-ohmic. We heated it up, so some surface states were saturated, pacificated, and we have got almost linear. And if we go further, then what happens? We get a rectifying kind of nature. Actually, what happens if you have high concentration of defects in the band gap, you can actually pin the Fermi level. Okay, so this where the Fermi level is pinned, where the Fermi level is positioned, depending upon that, you decide whether the contact will be ohmic or non-ohmic. So that can be tailored by, that can be controlled by surface stress configuration. And this is IV characteristics of the same similar sample, and it shows this kind of negative differential resistance. So if you have a negative differential resistance, you are part of isotonic tunneling current. Tunneling current gives you microwave oscillations. So this kind of structures. I have just tested this Baker's photograph here, because look at the peak of this and my IV characteristics, they are very similar to each other. That's why I couldn't restrict myself from testing this. So the name of this should be given as Baker characteristics. So this actually shows two things: NDR, negative differential resistance, and hysteresis. So if you have hysteresis, then you can use it for memory devices, right? The magnetic hysteresis is used as memory devices. The last one is on that memory device. no, that's but one. Here also I am not going into the details, time is almost up. So the surfaces within the band gap can lead to controllable, actually light controlled hysteresis, and we have tried to explain this hysteresis by a simple random walk model. Now, if you inject an electron in your PN junction device, then for defect free system, what happens? It processes the junction, right? Now, for junction containing a lot of surface defects, there are two possibilities. One, it will be captured at an empty state, or it can knock out one electron from already captured state, and it goes there and sit at the same position. Or it can happen that it just doesn't interact with the defect. So that is equivalent to the previous one. So there are two possibilities: either it gets captured or it doesn't get captured. So these are the two possibilities. So it's a two random walk problem. So what happens if it gets captured? Then within a junction, one electron is being captured. That means the junction is acting like a capacitor where a charge is being stored. So there will be some potential developed. So that will oppose injection of further electron. So a potential barrier will be developed. So when you are actually moving in one direction, you are increasing the voltage. We call it the trace path. In the trace path, trapping will be the dominating phenomenon. Your electrons will be kind of this thing, and you will have kind of voltage developed there. And when you are in the other way, your trapped electrons will get detrapped, and the voltage will decrease in, the value increase with decreasing current. So correspondingly, you can just calculate and get this kind of hysteresis curve. And the theoretical one is the red one by this random walk problem, and the black one is the experimental one. They are very close to each other. If you add some parameters, you can match them. And the last one is, as I told you, that if you can make silicon is emitting in the infrared. Not only that, there is a specialty of silicon. If you go to Chandni market for light emitting diodes, you will never get a silicon based light emitting diode. Why? Anybody? The light emitting diodes will be of gallium arsenide, indium phosphide, indium helium arsenide, but not of silicon or germanium. Anybody? Why? Sorry? No, that's not very good. Yes, silicon has got indirect band structure. That means, when an electron in the conduction band wants to come to the valence band edge, not only the energy the photograph that I showed was of silicon, no? Just one minute. I'm going back. This one. Look, these are silicon analysis. And these are showing green light as well as red light. Not from gallium arsenide or any other. This is silicon. In bulk, they are indirect band gap. But in nanoscale, they behave like direct band gap because of the uncertainty principle. Now, if we look, photoluminescence is fine, but we cannot treat it as a device. But for a device, what we need, you have to make a device like electrically controlled device. You can't do, if you want to get light, you are switching with UV lamp and then you are getting light. There is no point in that. What you want to apply some voltage and you get some light. So that is done in light emitting diode. So this is the structure of the light emitting diode. We have made it on laboratory. So this is the base silicon. This is the nanostructure silicon. Then metal. Now you can see here, like the photoluminescence of two colors, here also you can just see. We have made actually two devices, one with gold, the other one with silver. With gold, we get red light. With silver, we get a little bit towards orange, whitish light. And if you look at the spectrum, gold emits in the 630 nanometer and 701 nanometer. But in silver, we get almost 3 peaks. This 701 nanometer is present in both. Additionally, with this 28 is now 604, and additionally we get a blue band. Okay, in this. Why it is so? So it's very simple also. Here, I told you that if you have surface states where you are injecting your electrons from outside by applying voltage, can be controlled. For silver, the solid solubility of silver in silicon oxide is very silver on silicon oxide containing silicon nanocrystal. The probability that the silver atoms will go closer to the core of the nanocrystal is higher than has got lesser solid solubility. So in case of silver, the case can be the oxide, effective oxide layer thickness is much smaller. But in gold, the oxide layer thickness is much higher. Okay? So when you apply certain voltage, the oxide layer, oxide is insulated. No? If you apply some voltage V, some drop will be at the oxide layer, and the rest will be applied to the actual nanocrystal. Okay? So for gold, what happens? You apply 5 volt, but the actual effective voltage that is appearing at the nanocrystal will be say 2 volt. But when you are applying the same voltage to silver, you are applying 5 volt and you are actually getting say 4 volt. Okay? So effectively, what happens with the same voltage for silver, you are actually injecting electrons at the higher level. And when you are doing the same gold, you are applying electrons to surfaces within the band gap. So within the band gap means you are getting smaller energy light, which is falling in the red region, and for silver, you are getting band to band transition, trap to band transition, and trap to trap transition. All possible transitions are there. So 3 different things we are getting. Now to check this framework, what we are proposing, we perform another experiment. We took this thing, gold, and applied higher voltage. Okay. Then what happens with the same voltage? We didn't get 3 peaks in gold, but when we are applying more voltage, then in gold also we are getting 3 peaks. That means what we are assuming that probably we are in a correct direction. Okay. So in this way you can control the color of the emission by controlling
some commercial equipment manufacturer, so that if other places
Well, that I have one here, but it can be done. I mean, it can be done by any physics teacher actually. I mean, with reasonable workshop, one can easily make.
It costs around
Less than 10,000.
very low cost device.
Yeah, very low cost. And it's really, I have shown everything. You can actually get the band diagram. Yeah. Actually, I am associated to IIEST also. In IIEST workshops, I put one this experiment. And also, probably Mathieu or somebody else, I don't remember, suggested modeling the same thing for defects test or something like that. That's exactly
Yes,
or something like that. So that these things can be done easily. And also you can, by changing the cost function, if you change it to square wave, then instead of natural equation you get Fields equation. So how the band gap changes, I mean whether the first band gap is equal to the second band gap, or all the band gaps are equal or decreasing towards continuum, all these things can be simulated.
other questions? Yes, sir.
I would love to get questions from the young population.
So it seems if there are no such questions, let us thank the speaker. Ask all your classmates to come to the Colloquium. Now everybody is coming. That is very important.
Just one thing. If you feel shy here, you can ask any question and then put it here. My email is there, so don't hesitate to write an email if you have any questions.